So hello and welcome to our second Physics 157 lecture. And this is my second time giving this Physics 157 lecture because I managed to screw up the recording this morning, but that's okay. This is extra practice for me lecturing, and so sometime I'll be really good at lecturing. All right, so I'm going to share my screen. We can see the slides. Great. So just a couple of announcements. The only one relevant for this recording is that I'll have office hours today, Friday, and every Friday, 3:30 to 4:30 p.m. There's a Zoom link on Canvas that you can find. If you're not able to participate, or you weren't able to participate this morning to use the iClicker, don't worry about it. I'm not going to count the iClicker for today. What I told the class today was that hopefully starting on Monday, I'm actually going to have an emergency option where I'll be live streaming the lecture simultaneously to a YouTube channel. And so if you have technical difficulties with Remo during the lecture, then you can actually still participate by just going to that YouTube stream. And then you can come back when things get sorted out, or just watch the stream and participate in the clicker questions. Okay, so I'm going to skip these things. I talked a little bit about how the course works. So basically, every week is going to be similar. Before the weekend, we'll give you some pre-reading assignment. And so that'll just be in the assignments. It'll be a reading assignment and quiz. For next week, you have two because there was a logistical one and one about material. And so this is just us saying, okay, read these parts. It's going to be your first exposure to the material. And we don't need you to understand everything in the pre-reading. We just want you to have some exposure and to think a little bit about some simple aspects of the material before the classes next week. We give you reading questions in order to help focus you on the things that we specifically want you to think about before the lectures. And so that helps you prepare for the lectures in the following week. Then we have our lectures. And so we're going to go through whatever we think you need to know from this section. And sometimes there are a few things that are not in the textbook. If you need to know it, we're going to be talking about it in lecture. And we're not only going to be talking about it, we're going to be giving you some questions to think about. So they could be multiple choice clicker questions or discussion questions. And so we'll have this chance for you to process what you're learning in the lecture. Each week, we'll also have a tutorial. So once you've learned some of that lecture material, then we'll want you to apply it to some lengthier problems. So tutorial questions are similar to the questions that you're going to find on midterms or exams or in your written homework assignment. But you'll be working on those questions with a few of your classmates, and you'll have a TA there who will be able to help you if you get stuck. And so you'll be guided through the types of questions that we're going to expect you to be able to do in the midterm, in the exam. After the tutorial, each week we're also going to give you a homework assignment where now we go off and you have some problems to do on your own. Of course, you're still welcome to talk to your classmates about the questions. We'll even have on Mondays and Tuesdays, starting 2 weeks from now, some question and answer sessions about the homework where we have some TAs available. So you can actually go, it'll probably be using Remo. We'll go into the room. You can find some people to work with. You can talk about the questions and the TA will be there to help you. Okay. And then finally, we'll have quizzes actually every week. If you hand in a homework, then following up on the homework, there'll be a short multiple choice online quiz. And it should be very straightforward if you've spent the time to do the homework and understand it on your own. These are just questions to consolidate what you've learned. We'll have 2 midterms during the term. These will be a mix of multiple choice and written questions that you'll upload by scanning to a single PDF. And finally, we have the final exam. And so this is more for people in the class, but I'll go through it anyways. if you're participating in our Remo classes, then there's a few different ways to answer questions, or sorry, to ask questions. One of them is to type them in the general chat. And these will be monitored by our TA, our lecture TA, Tim, who's going to keep looking at that and can answer your questions in real time through the chat. So we're going to make sure that we reserve this general chat for questions only. So please avoid just making kind of random comments or jokes or whatever. Let's keep the general chat just for questions, and so that the chat doesn't get overwhelmed, and so the TA can find the questions and answer them and people can see the answers. The other thing you could do is type a question in the Q&A box, and that would be something that I will check periodically to see, and I'll answer those things verbally. And finally, sometimes I'll pause for questions, and you can raise your hand if you want to ask your question verbally, and I'll try to remember. I have to get used to all of this, so I'm going to try to remember to more carefully monitor the Q&A and the raising hands so that I can answer your questions during class. Okay, so we're going to start. We had a clicker question. This was mostly to test out the clicker system, but it's an interesting question related to our course material, so I'll give you a chance to think about that. So if you're watching this recording now, then I would recommend pausing the recording and thinking about this question. Okay, so hopefully you've had a chance to think about it. You've committed to an answer, written it down. And so let's think about the question. A mercury thermometer sits in a glass of water. If the thermometer reads 20 Celsius, we can conclude that. Okay, and so I think a couple of these answers sound very reasonable. So normally when you put a thermometer in water and it says 20 Celsius, that means that the water is 20 Celsius. And so you might think that A is correct and the temperature of the thermometer should also be 20 Celsius because they should be the same temperature. And so you might answer C, both A and B. So that would be assuming one thing, though. That would be assuming that that thermometer had been in the glass of water for a long time, long enough so that the temperature of the water and the temperature of the thermometer would be the same. In the question, we don't actually tell you that. It just says if a mercury thermometer sits in a glass of water, we can conclude that. So if you don't really know how long it's been there, if maybe someone just took the thermometer and it was at room temperature and puts it in a glass of ice water and then reads the thermometer immediately, the thermometer might still say 20 degrees Celsius because the thermometer is 20 degrees Celsius, but the water could be colder than 20 degrees Celsius, and it just hasn't been long enough for the temperature reading on the thermometer to change, for that mercury to cool down. So the answer I had in mind here was that the temperature of the mercury in the thermometer is 20, and that we can't conclude A, so the answer would be B. And we're going to talk a lot about this process of approaching that situation of thermal equilibrium where the temperatures would be the same. Okay, so now let's get to the main content for today's lecture. So last lecture, we carried out one of the most boring demos that's ever been carried out in a physics class in the history of physics classes. That was that we looked at a brick and eventually we talked about that brick. And so the point of that demo was that there was nothing going on that we could see. But because we'd taken a brick out of a cooler and then placed it on a table where the surroundings were warmer, there actually is a lot of interesting things that are going on. And so if we actually were to zoom in, if we were able to see the molecules in that brick, then we would notice that they're not just sitting there. There's all sorts of motion and interactions with the surroundings. So it's a very, very complicated system. And really, our topic for the first part of this course, thermodynamics is basically the subject of trying to understand how can we summarize all of this crazy stuff that's going on at the microscopic level and describe it in terms of a few simple quantities. So things like temperature, pressure, and so forth, these are quantities that summarize average properties of many, many atoms or many, many molecules. And the subject of thermodynamics that we're going to be learning about is basically how we understand the behavior of these macroscopic quantities, temperature and pressure and energy and heat flow. We can understand the behavior of those without understanding exactly what all of the individual molecules are doing. Okay. So let's get started. A really good starting point for studying thermodynamics is thinking about energy and the conservation of energy. So a lot of the subject is really just about how energy is being transferred between different forms, between different parts of systems. And so let's start by just remembering what is energy and what is the conservation of energy. So the idea of energy conservation is that if you have any system, any physical system, it could be a solid object or a liquid or a gas, or even just some part of outer space, some vacuum in outer space, or somewhere in the middle of the sun where you have a plasma, or inside a nucleus. So any kind of physical system, if you look at a part of a physical system, then there's always some number that we can associate with that physical system or with any part of a physical system. And we call that number energy. And the property of energy is that if you have an isolated system, then that energy does not change. If you have an isolated system, the total energy does not change. If you have a system which is interacting with an environment, then any change in the energy of the system is compensated for by a change in the energy of the environment. And so if the system energy increases some, then the energy in the environment has to decrease. And so you should think of energy as being this quantity that you can't get rid of. It can go from one place to another. And weirdly, it can actually go from one form to another. So as you've learned in high school, you can have kinetic energy, which has to do with the motion of objects. And sometimes that can be transformed into potential energy, which has to do with the configurations of objects. Okay. So in thermodynamics, what we care about a lot is the microscopic kinetic energies and the microscopic potential energies of atoms and molecules. Things like temperature, we'll describe later on, are related to the averaged kinetic energies of these microscopic components. Okay, so just a little bit of trivia. Back some time ago, so people were aware of conservation of energy for many years, but it was eventually actually understood why energy is conserved and exactly in what circumstances energy is conserved. So we actually now have a really deep understanding of energy conservation thanks to one of the greatest physicists of all time. And I asked the class this year and last year and the year before to guess, who was this physicist that fully understood conservation of energy. And actually this year, there was actually one person that knew. In previous years, basically almost no one had any idea, and nobody got it right. And then I actually even put up a picture of this person that discovered this amazing piece of physics. Here's the picture. And in previous years, it still took everyone a long time to come up with the right answer. So a lot of people said, oh, is it Marie Curie? No, the person is Emmy Noether. And so she lived in the 19th and 20th century, and she proved what's known as Noether's theorem. And this really explains not just energy conservation, but all sorts of conservation laws. So we have other conserved quantities like momentum and angular momentum and charge. And Noether basically understood that you will have one of these conserved quantities when your physical system has a property known as symmetry. And so this is a diversion for this lecture. If you want to learn more about that, please come to office hours sometime or ask me after class, and I'd be really happy to tell you about symmetries, their relation to conserved quantities, and Emmy Noether's work. Okay, so let's get back to conservation of energy, and let's think about how does this apply to our brick, to our silly demo that we did last class. And so what we said was we took the brick out of the cooler, it was cold, and then it starts heating up as it sits on the table. And so one thing to understand is really, what does that mean? What does it mean that it's heating up? And we can understand it at a molecular level. So the cold brick has molecules that are not just sitting there, they're moving around. So unlike a liquid or a gas, the molecules are mostly fixed in place. That's what it means to be a solid. So they're not moving all the way around the brick, but nevertheless, all of the molecules in the brick are constantly moving randomly, so kind of vibrating around their average location. And nearby molecules are colliding with each other and interacting with each other. What it means for something to heat up is that from outside, extra energy is going into that brick. That can happen through collisions with air molecules, through radiation hitting and being absorbed by the brick, various mechanisms. But what happens in the end is that those molecules start vibrating faster. And so you're adding kinetic energy to the molecules at the molecular level. So that's the difference between the cold brick and the hot brick. When we say hot or cold, it's really just a statement about energy at the molecular level. Now, an interesting thing is that even though in our demo on Wednesday, it wasn't very obvious that anything was happening, there are actually observable consequences of the fact that these molecules are moving faster and that we've added energy at the molecular level. So it's a good time now to stop the video and think to yourself about what are some of these macroscopic properties of objects that we might be able to observe where we could tell if an object is being heated or being cooled. Okay, so hopefully you've paused the video, you've made a little list of properties that might change if an object is heated or cooled, and now I'm going to talk about some of those things. So there are certain situations when these macroscopic changes are very obvious. For example, if you have ice and then you add heat to it, it may not change initially, but at some point, if you add enough energy, then not only do the molecules vibrate faster, they end up completely changing to a situation where the molecules can now escape from each other and move around the substance. And we know that as a phase transition. So there's some situations like that where the physical appearance of a material completely changes because of the increases in kinetic energy. There are more subtle things. Even if you heat up a piece of ice and it doesn't melt, if you have a fairly accurate measuring device to observe the dimensions of your ice or of some other solid, you would actually notice that as I heat up a solid, it generally expands a little bit. So it generally gets a little bit larger. And if I cool down an object, it generally gets a little bit smaller. Other situations where you have a dramatic observable change would be if you think about a very hot object. So say a metal that is heated up to a very high temperature, then we know that actually the metal will start glowing. We'll see it turn red, and then if you heat it up more, it'll be more orange, and then eventually it could be white hot. And so that's a property where, okay, it's obviously changing temperature because it's changing its physical appearance, it's getting brighter. Well, there's a more subtle version of that that was even true, even present for our brick the other day. Okay. So in visible light, something has to be very hot for us to observe the radiation that's being emitted. But for cooler objects, they're actually still emitting lots of radiation, just not at the wavelengths that we can see with our eyes. But if you have an instrument that's able to see those longer wavelengths, so an infrared camera specifically, then it would be almost as dramatic to heat up our brick from cold temperatures to warm temperatures as it is to see a metal glow red hot and then white hot. You just have to look at it in the right range of wavelengths, and then it's very clear visibly, or using electromagnetic radiation, it's very clear when the temperature is changing. Okay. So we could go on. It really turns out that almost anything that you measure about an object, almost any macroscopic property, will be affected by temperature. So pretty much every answer that you could imagine would be a right answer. The conductivity of metals, or the compressibility of a material, or all sorts of things that you could imagine measuring, almost all of them will actually have a dependence on the temperature. Okay, so I've got a couple of picture slides just so you can see. This is just things I said already. So the solid will get a little bit larger as it gets hot. It's more obvious with the gas in a balloon. The mercury in a thermometer expands as the mercury heats up. It expands more than the glass expands. And that's why you see the level of the mercury rise in the thermometer. As the whole system gets warmer, that volume of the mercury increases and causes the level inside the glass tube to rise. Okay, and then this is just a depiction of the infrared radiation changing as you change the temperature of the object. Okay, but more impressive than my admittedly not very skilled artwork is to actually see this happen. And so yesterday I actually went into the physics building to the what would be our physics 157 classroom, and I did a demo with an infrared camera, and so I'll play that now for you. Okay. So I don't think you can hear this, but I'm going to talk through it. And so basically what you see is that you've got an infrared camera set up here. It's looking at me and a couple of aluminum bricks. And this one is hot. It's on a hot plate. And this one is cool. And then this is the display for the infrared camera. And you see the hot one is just glowing really bright. I'm also glowing very bright because I was warm. I had this long sleeve shirt on. It was warm in. No, but even just because of my body temperature, I'm emitting lots of infrared radiation at the wavelengths that this camera is emitting. And then this one is cooler. This is like cooler than my body. It's room temperature. And so you see, oh, well, you saw that it was not glowing nearly as much as the previous one. Okay, let's find the slides again. So actually, I've had a little bonus demo that I did as well, which is very cool. So this connects to the idea that you learn in high school when you have inelastic collisions that you lose energy to heat. So you probably just were supposed to believe that before, that if you have two balls colliding or a ball colliding with the floor and it's not elastic, then you can actually end up having a kinetic energy of the object transferred to heat, which we now understand as this microscopic kinetic energy happening at the molecular level. Okay, and so actually I wanted to demonstrate that using the infrared camera. And so what I found in the demo room was a big lead sheet and a big heavy lead ball. And so in the demo, which is very short, I'll show it to you. I'll probably show it to you twice. What I do is I throw the ball at the lead sheet. And so let's watch that now. Okay, so there's the ball. I'm picking it up. Have a look at the camera monitor. Okay, oh, that was a very, very short demo. So hopefully what you saw is that after I threw the ball onto the lead sheet, there was actually a bright spot on the lead sheet. So let's watch that again. So you could actually see that there it is. Okay. And actually, one more time, the ball I think actually gets a little bit brighter. I'm not sure if that's true, but definitely there's a bright spot on the lead sheet after I throw the ball down there, and the ball I think is glowing a little bit more. And so that just shows you that we've somehow managed to increase the temperature of the system. So we've transferred kinetic energy from the ball. You have this inelastic collision. Now some of that energy gets transferred to the motion of all the molecules in the lead sheet. And as a result of that heating up, it emits brighter infrared radiation, and we can see it as a glowing spot on the camera. Okay, so I think I really like that demo. All right. So what I'm going to do in the next video is to place the hot block. So I still was there in the same room. I had that hot aluminum block and I had the cool aluminum block. And what I'm going to do in the next video is actually to place the hot block onto the cooler block. And we're going to watch what happens using the infrared camera. So first, maybe just pause briefly and think about this question. This is a pretty obvious one. What happens if we put the hot block in contact with the room temperature block? So I'll give you a moment to think about that, possibly pause the video. Okay, so I think this one is pretty obvious that, that there is going to be some heat flow from the hot block to the colder block. And as long as that one block is hotter than the other block, then there's going to continue to be heat flow from the hotter block to the cooler block. And so heat will flow, the hot block will cool down, the room temperature block will warm up, and eventually they'll be at the same temperature. Okay, and then maybe they're still a little bit warmer than room temperature, and heat will flow from the block to the air, the blocks to the air, and then eventually everything's going to be at room temperature. Okay, and so we have this approach to equilibrium. But what does that look like with the infrared camera? And so I want you to actually make a prediction. Remember what the hot block looked like on the infrared camera. It was all glowing brightly, and then the cooler block was you could see it, but it was dull. It wasn't glowing much at all. And so I want you to take a moment to make a prediction, maybe actually make a sketch of what you think will happen. Let's say draw one picture right when you put the first hot block onto the cooler block. What does it look like in infrared? Then what does it look like a few moments later? And then what does it look like after a long time? Okay. And so then we're going to watch this demo. Okay, so here we go. All right, so here is our presenter. I'm just here describing what I'm going to do. I already said that. There's safety equipment that I have there, just in case. Actually, I'm going to pause it for a second, just so you notice. One interesting thing is that once I put the visor down, you can no longer see my face in the infrared. So the rest of my body is bright, but the visor looks dark. And partly, I mean, that may be because the visor is cooler than my body, but actually my face would be giving off all this infrared radiation. And so if the plastic were transparent to infrared radiation, then it should actually look bright on the infrared camera. So you should see that radiation from my face, but it looks dark. And so that tells me that even though the plastic is transparent to visible light, it's not transparent to infrared light. Okay, so that's sort of an aside. Let's start the video again. Okay, so let's specifically watch in the video. So there's me grabbing the hot block and placing it on the other block. Oh, and it's sliding around a little bit here. Okay, and so hopefully I'll get out of the way in a minute. Get out of the way. Okay, there we go. So let's see. So it's actually fairly dramatic. You can see that lower block, the brightness is working its way down and working its way down and working its way down. Okay, please get out of the way. So if you think about it, then that makes sense, because the heat would flow from the top block into the top part of the lower block, warm that up, and so that should start glowing first, and then the heat from the upper part of the lower block works its way down to the middle of the lower block and then to the bottom. And so you have this, you can really see the heat flowing, or we can't actually see the heat flowing, but we can really see the local changes in temperature as the heat does flow. So as the different parts of that aluminum warm up, they start to glow more and more. All right. And so let's go back to our slides here. Okay, and here's my artist's rendition of that. So just in case you had a hard time seeing in the video, and things are horizontal in my picture, but we had the aluminum block on the hot plate. It was glowing a lot, and then we put them next to each other. And after a little while, I mean, initially it looked like this. After a little while, then you saw that this one started glowing, and eventually the whole thing was glowing. Basically, in our camera, it all looked very bright. So I think what happens with that infrared camera is once things are above a certain temperature, it just saturates the camera, and it looks very bright. And so it really looked like this was bright, and then everything was bright. But if we waited a longer and longer time, as those blocks came to room temperature, they would dim, and then eventually they would look like this. And eventually they would both look like this once they were in equilibrium with the room temperature, with the room. Okay, so just have a few slides left. So just kind of summarizing what happens at a macroscopic level, and the kind of language we use about this energy being transferred from one thing to another. Okay, so the idea of temperature, you can talk about that. You can sort of define higher temperature, lower temperature, equal temperature based on whether energy flows from one object to another. So what we say is that if we bring two objects in contact, there are three logical possibilities. One of the possibilities is that no net energy flows from one thing to the other. And in this case, if we notice that, then we would say those two objects are in equilibrium with each other. And we say that they have the same temperature. So that's one way of defining what it means for two things to have the same temperature, if you notice that no heat flows from one object to the other object. The other possibilities are that heat does flow from one object to the other object. And what we would say in that case is that the object where the heat is flowing from has a higher temperature, and the object where the heat is flowing to has a lower temperature. Okay. So heat is really just another word. It's just energy, but it's specifically this microscopic kinetic energy. So when energy flows from one object to another through this microscopic process of molecules colliding with one another, we say that that is a flow of heat. Okay, so there's nothing going on macroscopically, but nevertheless, energy is going from the brick into the balloon. Okay, so these are your basic options. And there's a really important result. It's an experimental observation, and it's called the Zeroth Law of Thermodynamics. I guess because they'd made 1, 2, and 3, and then they thought, oh man, this one's really important. We shouldn't call it the fourth law of thermodynamics. It's actually really fundamental to thermodynamics. So we'll call it the Zeroth Law. Okay, so what does the Zeroth Law of thermodynamics say? So it's about these kinds of experiments. It says that if I find two objects which are in equilibrium, so that no heat flows from one to the other, and then I find a third object that I find to be in equilibrium with the first object, then I will find that that object is also in equilibrium with the second object. So if these two are in equilibrium and these two are in equilibrium, then both of these are in equilibrium. Okay. And that's actually kind of crucial to the idea that you can assign a temperature to objects. If you if you if you didn't have this, then it wouldn't really make any sense to, that there would just be one number that determines whether heat flows or not. Okay. So the fact is that in the end, there's actually just one quantity, the temperature, that we can define that will determine whether heat flows from one thing to another. And so if that's true, then this must be true. Okay. Because then, if these two have the same number for temperature, and these two have the same number for temperature, then these two must also have the same number for temperature. And so all of them would be in equilibrium. Okay. So far we haven't really said how to define that number. We haven't said how do we assign a number to temperature. We've just said how do you tell if one thing has a higher temperature and one thing has a lower temperature by looking at whether heat flows one way or the other way. So next class, we're going to talk more about how do we actually define a number for temperature. And it's basically going to be just using some of the things we talked about in this class. We'll actually choose some kind of reference system, and we'll choose some macroscopic property of that reference system that changes as temperature changes. So like the height of mercury in a thermometer. And then using that macroscopic property that we can observe, we can assign different values for temperature. So we might say, okay, if the mercury is here, we'll call that 0. If the mercury is here, we'll call that 50. So that's all we have for today. And hopefully that's clear. If you have questions, post them on Piazza. And otherwise, we'll see you on Monday.